I'm Rongjun Cui from University of Toronto, and I'm going to present our work about catching Iago bugs in legacy applications. This work was done with Professor Lianying Zhao from Carleton University and Professor David Lee, also from University of Toronto. Let's get started. Recently, isolation techniques are designed to run secure sensitive tasks on an untrusted operating system, because trusting the OS means to trust not only the kernel, but also device drivers and service daemons that run as root in the system. It is unnecessary to secure all those privileged components when the user's goal is only to make sure a trusted process can run securely. So, by running an application inside an isolated environment, the OS no longer has access to the application's memory. However, the original syscall mechanism used by the applications to access OS services also won't work in this scenario. Thus, many isolation techniques adopted a solution to create an OS forwarding layer, short as OFL, which forwards syscalls to the untrusted OS and copy back return values to the application's address space. Forwarding syscalls to the untrusted OS exposes an attack surface from syscall return values. Legacy applications usually trust syscall return values, and it is fine. But when they are ported to an isolated environment without modification, Iago vulnerabilities could suddenly appear due to the threat model change. Iago attacks abuse the trust of legacy code to compromise the protected process. In this example, the original developer assumes read syscall returns a value that won't greater than max size -1 based on the menu page. However, if such code gets ported to an isolated environment, OS is no longer trusted. So it can actually return a large value and trick the application to override an arbitrary byte to 0. If the attacker can somehow guess the memory layout, he could turn some important flags to 0 and change the application's behavior. Therefore, it is necessary to identify and remove Iago bugs in legacy code before they are getting ported. So we developed a tool called Emilia to do this task. It is a fuzzing tool which can fuzz a legacy application through syscall return values. Rather than replacing the kernel, Emilia intercepts syscall made between the application and the standard OS kernel. Note that Iago bugs can take various forms. We consider it the worst when code or data pointer can be corrupted. So our work focused on memory corruption bugs. The most obvious difference between our fuzzing and traditional fuzzing is the fuzzing target. For traditional fuzzing, the target is input to the application or function, such as argument and configuration files. They can be determined before actually doing the fuzzing. However, when we passively fuzzing syscall return values, all syscalls are our potential fuzzing target. The number of syscalls and their sequence are not deterministic and can be affected by the fuzzing process itself. And some syscalls won't appear after the previous syscall get fuzzed. For example, in this code snip, fstat returns 0 in the vanilla execution. So fstat is our only target syscall at the beginning. But after fuzzing the return value of stat to be non-zero, the log function in error handling path will be called and the write syscall inside it will be invoked, which does not occur in the vanilla execution of the program. If we just blindly fuzz all the syscalls, we may be less likely to fuzz those extra syscalls repeatedly, because we can't control which execution path will be triggered. Therefore, we build a stateful fuzzing tool that can deterministically explore those newly occurred syscalls. Here I will provide a live example of how our stateful strategy works. In each iteration, we will store some fuzzing state into a reference list. Each element in the reference list provides a guide for mutating one syscall invocation. It contains the target syscall's name and its stack hash to help the fuzzer identify this syscall invocation. We use stack hash as the identifier because it can represent not only the location but also the context of the syscall, which somehow reflect how the syscall will be used, how the return value will be used. And other elements in the reference list include a field index that indicate which output field of the syscall should be mutated, and a value used to fill that output field. Note that a syscall could have multiple output fields. For example, field 10 and field 11 are two output fields of syscall 1. So the fuzzing process starts from each syscall in the vanilla syscall sequence. In this case, syscall 1 and 2 are two vanilla syscalls. We first fuzz syscall 1 and initialize the reference list with stack hash, the first index of the first output field, and the first value picked from the output field's value set. After the application finished a crash, the tool will check if new syscall invocations occurred. In this time, no new syscall invocations found, so we start the next iteration with other values and fields. After a failed try on the syscall 1, we pick value -1 for field 11, and two new syscalls appear. We then start to analyze syscall 1.1. To make syscall 1.1 occurs in the next iteration, we'll try to replace the previous execution path by mutating syscall 1 with its value recorded in the reference list. After finish analyzing syscall 1.1, we move to syscall 1.2. And then we go back to syscall 1 and continue trying the remaining values. Finally, we will move to syscall 2 and so on. We pick fast value from pre-created value set corresponding to each output field of each syscall. Each value set contains min, max, and some random values. We also extracted some values from static code analysis to try to increase the syscall coverage. We found a total of 51 memory corruption Iago bugs in 17 applications. We found at least one such bug in 16 of them. We classified the Iago bugs found into 5 types by the nature of semantics they violate and how those semantics can be checked. Let me explain those types. Static semantics can be checked independently to syscall arguments or history. One example is the range of error code. And this semantic can be simply verified against a predefined error code list. We know that many syscall will return a positive value on success, and C library will move the negative return value to error none and set the corresponding return value of the corresponding syscall wrapper function to -1. However, it only happens when the return value is greater than -4096. This example of Redis uses accept syscall return values to index a FD array in line 11. Before doing that, Redis did some checks in line 2 and line 8. However, a crafted negative return value that less than -4096 will pass the check in line 2 and eventually cause an out-of-bound indexing in line 11. Local semantics are only dependent on the arguments that are local to the syscall. For example, the return number of bytes processed need to be less than or equal to the specified buffer length as an argument. Read link, read, and receive message are such syscalls. And this is the same example I explained before. And some stateful information involved in syscalls is supposed to be exclusively controlled by the application. The application may make assumptions on return values regarding such information based on the previous invoked syscalls. Syscalls like equal weight will return user data corresponding to the port FD. The user data should contain the same data as was stored in the most recent call to equal control. And in this example, FD is a user store data returned from equal weight. like TBD, again use return FD to index an FD array. FD array is actually placed before equal events. That means a properly crafted FD could make FD array FD point to equal events. And we assume the attacker fully controls the equal event's content because it is an output buffer of the syscall. So the attacker can make handler pointer in line 14 points to any address he wants. And then this address will be interpreted as a function pointer and get called in line 8. Thus, the attacker can hijack the application's execution. For unauthenticated channel, some multi-component applications rely on the OS to establish a communication channel via pipes. The receiver end may use Syscall-like read to retrieve data provided by another component. And when no authentication is performed, an Iago may result. Notice it is different from untrusted payload getting from file or network, as both endpoints are part of the trusted application. And finally, external semantics depends on information external to the application. Examples includes randomness, time, and file size. Some lexicode assumes it owns an unencrypted file exclusively, which is not true even under a normal threat model. So as a result, about 80% of the Iago bugs we found are caused by local and static semantics. Fortunately, the OFL could simply check the return value against a predefined range or other constraint to mitigate them. Checks for stateful semantic violation require logic to maintain a parallel state with untrusted OS. For example, keep track of Syscall's history. An alternative is to patch the application to no longer be vulnerable. We found that all 6 applications that contains an equal weight bug can be configured to use other polling syscalls, such as pull and select, for compatibility reasons. For external and unauthenticated channel semantics, we argue that the application should not make assumptions on resources that it does not control or keep track of. They should use cryptographic methods to protect sensitive results and metadata. To understand if our findings apply to real-world systems, we manually reviewed the OFL implementations of 6 isolation framework and TE-ready applications to see how do they mitigate the Iago bugs. We found that none of them checked the negative error code, and most OFLs lack of verification for local and stateful semantics. Even more, we found that there's a Iago bug inside TE-ready application and OFL themselves, although they are designed not to trust OS return values. We have reported the bugs found in Oslo to Google, and they have been patched now. In conclusion, we have developed Emilia to help identify Iago bugs in legacy applications. We discovered a total of 51 memory corruption Iago bugs in 17 applications. We further classified them into 5 categories based on what type of semantics they violate. We also proposed potential mitigations for each of them. In addition, we analyzed some OFL implementations to show that Iago bugs could be a real-world problem. And that's all for my presentation. Thank you for listening.